Hello everyone. I worked on the IGM case, which was about DNA functionality. And today I'm presenting alone. I worked on the case, I didn't have any teammates. I tried to find, but I found that there wasn't many people who were willing to work on the same case. There are actually two another teams. Correct me if I'm wrong.
Four altogether, four.
Altogether, four. Okay. And the other teams had already enough people in the groups, so I finally decided to start working and start looking for teammates. So about the case, we had seven different files with DNA of different species. First of them was about contains the DNA of cow, one for sheep and one for pig. And I like to call this group the good one because this is something you want to find in the sausage as a DNA. And the other group is the bad ones. The first one is E. coli, which is a bacteria that can be found in all human bodies, but in lower with higher amounts. It could cause food poisoning or a disease. And the other two are the DNA of a cockroach and a sardine. As you can imagine, these are bad because you don't want to find them in the sausage. Just for a recall, the DNA contains four main nucleotides: adenine, thymine, cytosine, and guanine. I know, but one of the first questions that popped into my head was how exactly you can store a DNA data into a digital file. Does anyone of you know? Well, this is how it looks like. On file, the DNA is spread into genomes, and in the orange square you can see one genome, and everyone, each of it has its own ID, name, description, number of features, and the most important part for this kind of analysis is the sequence. You can see that the sequence contains different letters, and there are four letters. We have, for example, the letter A, which is representing one of the nucleotides, adenine, and guanine, and so on. This is a sample, by the way, from the during the analysis, you could see that this is just for an example. You could see that the DNAs of these species are really, really similar, almost identical for some parts. And this could the marked areas are different between them, and you can see that sometimes there are really small differences which would lead for some time. The first thing I decided to do is to compare the good DNA with the bad DNA and to get those genomes that are different, and I get it from the bad ones, and then search these parts into the sausage DNA, so that I could find if there is bad things into the sausages. Well, this is not really a good approach because of few reasons. One of it is because the length of the genomes are not always the same. For example, if you go back here, this is actually a sample of the sausage DNA, and the length of the sequence is only 51 symbols. And for example, for the other, it could be uh, about 1 million of letters. So they're not the same. And the other thing why this approach isn't really good is because it is really, really slow. And it's actually when I tried to run this approach, I didn't get any results. And it takes 10 hours, and I don't know how much more time it needs. So um, I didn't have much more time to go with another approach. But there was something else that I was really curious about, and this is the distribution of the nucleotides. And here you can see tables for the three group DNAs, and you can see that they're really, really similar as a distribution. So you can assume that the distribution into the sausage should be the same or almost the same, and it's not. So there's definitely something else in it. Um, it probably looks like the distribution as the E. coli because of the higher amount of G and C, which we can see in the good ones. But this is just an assumption. I think you can be 100% sure. But one thing that you can be sure is that there's something else in here. I wanted to show you the results of actually the winning team. One of the teams that was working on that same case won the competition, if I can say it like that. And what they did was first to add more data because
They were
only
professionals.
yes, because they're professionals. And they went with three different approaches and toolkits, and you can see the results here. I really like those graphs because I don't know if you can see it, but these are sausages, and this is the main ingredients get into the sausage, and you can see that there's really sheep and cow and a bit of pig, but into the little pie, you can see that there's definitely something else in there, and all three of them. The results shows that there's a forest and maybe there's some red. You can see it in light blue and so on. I just want to show you the result because it's really. That was from me. Thank you.
Questions? I have a question for Angel.
Yes.
Because we know that every case it's we are expecting not specific answer or specific solution from every case, but the smartest or the most useful solution. Because you are part of the jury, what is the jury factors that you are focusing when you are assessing the solution of the
First, the method. Part of the juries were the mentors, and they were specified. I'm not part of the jury, but I was in the charge of instructing the jury. And so it's not the same thing, but still the same. And what we wanted not to stress only is only the numbers. We, of course, we are data science. Data science field, we have to be precise, and it's important. But we would like the jury to vote up on original approaches and original ideas also. And the reason why we go through a jury approach instead of, let's say, measuring all the results is that by having a human expert read through all you have done is much better for the participant because they will give you feedback as well. So we want them to have score higher the creative solutions, as well as solutions that give practical, useful results. I'll put it that way.
Okay, thanks. Only thanks for your work. Now we will talk about our case. Sven will present some our requirements and data preparation tasks. Just a couple of words about the T.R.O.L team that they will be after us. They have worked for 2 days without sleep, and they have, I hope they will show the document that they have made around 20 pages. 20 pages. This was incredible for 2 days. And this was not a code. This was actually scientific based. Because everyone can copy paste one code, but this was with descriptions and everything. And I was really impressed. The other team, 404, was also made a very good documentation about their case. It was mainly online team. No, the other was okay. So our case.
So the Telenor's case was to investigate social structures through use of networks and graph theory. In other words, social network analysis. Why social network? Social network is one of the things that needs to be investigated to unlock our data potential. So we prepared and provided aggregated data of profiles and patterns. The data attributes were connections between A and B nodes and their states. So now I would
just a couple of words. I would like to add, what was our idea as what we wanted to see as a result was, and what we want to use in the future based on that is to see if there is something behind this data useful for us in the churn prevention in order to improve our scorecard, and also in the fraud investigation in the SNA part. So there was two main tasks. They'll talk about those tasks, but when we were showing this graph here, is that this was the thing that we explained to the teams when we entered in the data form. After they formed the team during the first night, because Paul explained there was a time for 1 or 2 hours where you're finding some friends or someone that you don't know, just like PCG. And if it seems that you don't like anyone.
Or nobody likes me.
Okay, but this was our explanation how the structure of this data set looks like, and we have given them a data set how this structure is communicated, how it's connected in another way, and they had to combine those two data sets, and in the end you see some very nice results. Of course, there was some additional tasks. They'll talk more about them. So let's invite Rocky.
So yeah, we are kind of afraid that although the name of our team was cool, nobody really gets it. So actually, we were trying to raise a bit of awareness. In data science world and technical world, artificial intelligence is super popular and super hyped. And that was leading at the year 2016. This was leading to a Rotterdam organization, which promised to the world, okay, we are having a new pretty cool algorithm. It's called temporally recurrent optimal learning. They've said that that's the future of artificial intelligence. That's the kicker that is going to boost everything. And they've started a launch party, not bigger than the one here. It was around 100 people, not more, and they explained what they are doing, just the main things about it. And after that party, a lot of scientific people, a lot of people involved in the artificial intelligence nowadays, have started tweeting about it. And their tweets were a bit funny, but the investors, the people at the business, didn't get it, so they invested about $10 million at that project. And when the time comes for those guys to present the whole solution, they said, look at it, it's true actually. There is no such algorithm. We just wanted to see how can we hype the community, how can we hype the business about artificial intelligence, and it worked. So I could not promise to you that they gave the money back. They just have done nothing and have hyped the business. And it was pretty good story. You should totally check out the details in internet. And there are also t-shirts in the context of that. And usually when you start to work on a data science project, you try not to sound like these guys. You just don't try to say your thing. You try to actually make a difference, actually create something working. So yeah, we really wanted to make this story popular, and maybe that was our chance because not too many people get it to the date. So about us, we are Team T.R.O.L, and I'm Christo, definition editor. We recently graduated as at master program for artificial intelligence at Sofia University. I am working currently as a machine learning developer at PaySafe, and we show
I'm software engineer at Business Solutions. I'm also open developer as well.
and we have, let's say, almost 5 years of experience in software development, plus minus a bit. And we are going to present you what we have done at the Datathon and what results we have seen. Some of them were pretty interesting, some of them were pretty disappointing, but that's how it happens when you have to deal with, let's say, real data. So, what was the case? The case was we have a social graph. It was representing an interaction between people, and those interactions were formed as a graph. So we needed to apply sophisticated graph theory and machine learning approaches and data science approaches just to find something interesting. But so the data was actually could be defined as big, but it was not actually a big data. Still, you can apply a lot of algorithms which could be applied to big data. There were unique nodes in the graph. Those are just the unique people at the communication graph. It was that number. Sorry. It was about that number, and the edges, so the interactions between users were more than one, actually almost 1.5 million. And the most important part is that each interaction was labeled as importance. The importances were low, medium, and high. So the task sounds simple and it sounds cool. And also, we had an extra domain knowledge. We had a group of defined leaders, and we needed to explain why are they leaders, what makes them important, and so on and so on. You will see a concrete tasks a bit later in this presentation. So now, there's the graph. As you can see, subscriber A is just an ideal person, and subscriber B is just an ideal person. Label is the importance, and the real flag event says, did that event occur on purpose or it was just an accident? So those are the leaders. Those are just IDs of people in the graph, and the flag says, are you a leader from group 1 to 6? More about the leaders and the groups later. For now, you just need to know that that's the data, and let's start. Okay, so what do we do with that graph? It's pretty interesting. Let's find something useful on it. But also, we had those tasks. So we needed to define two membranes at the core of the graph. Sounds nice. And we needed to define the leaders. At first, we needed to define them without knowing them. And in the end of the second day, we received them, and we needed to verify what's happening and to see what was our mistakes. And after defining the leader, we also needed to find clusters that contains the leaders and that are explaining the behavior of the leaders. And at the end, we needed to define some metric about closeness between group 5 and all the nodes in the graph, all the rest of the nodes in the graph. So now, we started by thinking about, okay, the structure of the graph is that. That's our domain knowledge. And as you can see, it's pretty awesome. You have a core, and you have two membranes. They do not communicate with each other, and it's super awesome. It looks like structured bed. And the first hype was coming to us. We were like, oh, so cool. And then we were like, okay, what actually is a membrane in the graph? And we've studied graph theory. We still didn't know what exactly is a membrane in the graph, but we decided to ask Google. So let's Google result. I'm not sure I can scroll here, but you have to trust me. There is nothing about graph theory with membranes. So after a while, we were a bit confused and we said, well, let's do something. Google doesn't know. Let's do something that we know how to do. Let's do some statistics. So we just decided to explore the graph and see if something cool is there. And we were actually now kind of not happy. We were like, okay, we don't have the knowledge to solve the task. But however, we started looking at it. And in 5 minutes, a colleague from us that actually was not on our team, but was working on the same task said something like, yeah, people in this network were interacting only to their mouth. And really, that is kind of true. Most of the users in the graph were interacting with one or two unique person, and that's it. So there are a lot of interactions, but most of the people was not involved in them, which made us think about the task in a different way. So we decided, okay, maybe the leaders are involved in more communication than others, and we decided to look at the graphics. And this was the first graphic that made us think that probably we are not that stupid. So that's actually the number of ingoing versus outgoing interactions. And if you think about it, you can see there is a pretty strong correlation between the number of interactions that you initiate and the number of interactions that you receive. And we were super excited about it because usually in real cases, if you see the correlation like this, it's more than 0.89. This means something. And first we were researching a lot about this correlation, and this made us blank for a while. And it appears that a correlation like this is kind of normal. So if you interact with 5 people, usually they interact back to you. And this correlation could be normal. But what we didn't see at first at the graphic, and it's more important, is that there are outliers. There are points that have zero interactions. So there are receivers at zero interactions. They only initiate interaction, and the other way around. So those points actually were interesting. And we decided, okay, let's do some statistics about them. And what happens here? We have a group of interactors only. Those are people who had only interacted, who had only initiated interaction, but had never received one. And there are also receivers. Those receivers have never initiated interaction. If we imagine that, so you go to somebody and say hi, and he never says hi back, or you are just a creepy guy that says hi to people and nobody says hi to you back. So this is strange. And now we see more clearly. Okay, we have two membranes. Interactor only is the first membrane. Receivers only is the second membrane. And the other person with, let's say, normal for a person interactions in the real world are the core. And we had some more interesting conclusions here. The first one is that the first membrane has only 15% of all nodes, and this is pretty cool because we expected the core to be bigger than the rest of the groups. Actually, the receivers only contain 54 of all nodes, which was a bit of a disclaimer for us, but we had nothing else to do. We believed that those are the membranes, and actually we verified eventually. So there was no direct contact between the receivers and the interactors only. So this made us think that the core is the users with the normal behavior, and the rest of the users are just membranes. So we decided that's about the correlation, and you can check this link out to see why it's considered normal to have such strong correlation between in and outgoing interactions. So now, we decided to decompose the graph at three partitions, two membranes, and a core. And we decided we need to do it faster, just remove those. But after thinking a while, we realized that this should be a recursive process because if you remove all of the receivers, some nodes, you remove also the interactions to them. So some nodes could be receivers again. So we decided to build this recursive process. We actually do it in 15 minutes. We argued if that's needed like an hour, and we are still not sure if it was a small dead star. But okay, we decomposed the graph and decided to solve the task. Still, it might be too overcomplicated. We still don't know. If somebody has an opinion, we'll be pretty happy to hear it after the presentation. So now, the tasks were to define two membranes and the core of the graph. We've done that. So let's define the leaders. But first, the membranes were a bit strange, and when you have strange data, it's usually interesting. So yeah, let's analyze the membranes. First membrane has the structure of a tree. Sounds too scientific maybe. It means that those are the people who initiated the interaction and the people who received the interaction. So we tried a lot of algorithms from the graph theory, and the best working at that graph at all was the weakly connected components. So looking at the weakly connected components of the graph, we realized that there are 979 connected components. One of them is pretty big, and the rest are actually small and kind of strange. Strange here is not a scientific word, it's just they just look out of the ordinary. So what we find out that the strange components was most of them contain a gateway. A gateway was, imagine you're a user and your only interaction in the whole world was to one another user. And we were group penetration, so all of us in this room were only interacting to, let's say, one another user. So that user were receiving interactions only from a few interactors on the nodes, and this was definitely a gateway in the sense of, let's say, internet connections. And those were pretty interesting about person behaviors. So we decided those are interesting. It appears they are more than we thought. And just remember, those things exist. You will see later. After that, we just decided to look for fraud patterns in the membrane 1 and 2, because when you have strange data, you look for fraud patterns. So let me clarify it here. Those I'm about to show you are not definitely fraud patterns, are not definitely fraud. It's just we thought there is an interesting structure that we can see here, so we need to check it out. It could be fraud, it could be community, it could be families, it could be anything you want. If you want to determine what are those actually, you need to have more domain knowledge, and you need to just pay attention on those and see what they are. We call them fraud patterns. We might be wrong on that, but they were just interesting. So imagine the red ones has only interacted to the blue ones their entire life. So those three red dots has never interacted with anyone else but those two blue ones. There is a reason to take that here in the context of money transactions, for example. This would be suspicious. So we decided to show you two of those, and fraud pattern in membrane to membrane 2 are those people that have only received interactions. And here, most interesting part are the red dot. So the red dot has only interacted with nodes from membrane 2. Nodes from membrane 2 are only receiving interactions, and the red dot had never interacted with anyone else but them. And this still it should not be marked as fraud, but it's kind of interesting that you have this and this or that. So the red dot has only interacted to a lot of receivers and nothing else. So we decided just to show you that. With a lot of more domain knowledge, we can verify what is it, why is it there, but for sure it's interesting. And now it's time to make some real work in the core. We have tasks to do. So the core contains 30% of all nodes and 68% of all edges. So we are happy with it. And when we received the prediction leaders, it appears that most of them, 98% of them, are in the core. Okay, perfect. So we have a job to do. We see at the core most initiators contact no more than 1 to 3 distinct receivers. As I told you, most of the people are communicating only to their mouse. Most of the receivers were contacted by not more than 2-3 callers. Okay, but if this was not true, then we could define the leaders. So now, we decided let's use something smart. We decided to use centrality measures, and the things that we tried to use were in degree. Those are just the numbers of received interactions. The out degree are numbers of initiated interactions. And eigenvector centrality is a bit more complicated. Think about it like that. So if I'm a leader with a good eigenvector centrality, this means that I'm communicated to another leaders with a good eigenvector centrality. So if I communicate with a lot of popular people, I would be the leader of eigenvector centrality. So if I'm Barack Obama and I communicate, let's say, to Donald Trump, to Michael Jackson, I communicate only to famous people, so I am also famous. That's the meaning of this. And we try to find the leaders. Let's say if you are with a high eigenvector centrality, then you are a leader. And we've drawn a rock curve. If you don't understand the rock curve, don't worry. So we've drawn that.
Nobody
And
does.
at first we were arguing about if it's the other way around. It appears it's not. Actually, that's the worst curve that I have ever seen. So I won't get too technical, but this rock curve shows us that the metrics defined before are not working. They are even worse than random guessing. So something was wrong. We were maybe building another Death Star, and we decided to keep it simple. Okay, what's more simple than those things that we have defined? It's just the number of unique people that you have interacted with. It's pretty understandable for people. I just have a lot of friends, so maybe I'm a leader. And we decided to just give it a try. We was not very positive about it, but boom. It appears that at first look of the graph, we could define the 83.5% of the leaders at the first level connection. And if you take second and third level connections, it was getting worse. So as you can see, what is first level connection? First level connection are the people I'm directly connected with. So I have, let's say, 10 friends, and that's my score, 10. And second level connections, I have 10 friends, and they have 10 more friends, so I have 20. But at getting in more depth, it was not going well, so we decided to use first level connections. We could actually do it better. We decided to apply a bit of supervised learning, and boom, we could do it better. We could guess 88% of the leaders with precision 80%. Don't think about it too much if you don't know what recovery precisions are. Just trust me, we've defined 88% of the leaders pretty easily. And the decision was just, do you have more than 8.5 connections, which is more than 8, more or equal than 8 connections. So you are probably not leader, and if you do, you are probably a leader. Okay, we could do it even better. We defined, let's say, more features of the nodes. So we applied supervised, that's a decision tree, and it's pretty easy to interpret it. As you can see, if you have a lot of unique connections, and if you are a gateway, boom, gateway is now important, you are totally a leader. If you are not a gateway, you might not be a leader. And if you still have not enough unique connections, but you are a gateway, that blue one here, it's showing you that if you're a gateway, you probably are a leader. Otherwise, if you're not, you should be connected with more people. This has a pretty good precision in recall. We defined 85% of the leaders, and 93% of precision means that we don't make a lot of mistakes when we say you're a leader. The possibility of you not being a leader if we say you are is pretty low. So this could be improved. This is actually a visual example, so you can interpret it, but with a sophisticated model, with more features, these numbers could be very close to 1. The max of those two numbers are actually 1. So now, we've defined the leaders pretty good, and we find 2 membranes. Now, we have to define clusters, and we have to solve the last task, which is pretty interesting. So the leader clusters. We decided to build another one, because sometimes complicated approaches are working pretty well on simple data. So yeah, we like Star Wars, and Death Star, and we decided to build one. And it was called like that. Don't overthink the name of the algorithm. It was 3 a.m. in the morning. We just used two words. This kind is a real word, an algorithm. Actually, everything is a real word, but
Trust me on that.
so just on that. We try to define clustering algorithm that would give us communities with one mutual friends, and we defined those formulas. This is scary, but not that sophisticated actually. The distance between two nodes is just defined as the weighted sum of the interactions between them, or if they are not directly connected, the weighted sum of their neighbors, of the paths to their neighbors, but only at level 1. So we've built a matrix. We tracked density-based
Just to make sure,
clusterization.
did everyone get this formula? Because it's pretty clear.
It's, okay, let's say it's, okay. Okay, forget about it. So those are just the weight of the labels that we had. Don't overthink it as well. And now, what we expected to do is clustering representative social group with one mutual friends, and maybe we have done that, but we expected at each such cluster to have one or two leaders or a few leaders, and we decided to measure it. So the similarity coefficient was telling us there are clusters that you are finding. They are not very good, but it's there something. And we decided to check, are the leaders actually good representing the clusters? And I remember Micho, a friend of mine, to check a library Python scikit-learn for a metric that says we are doing well. And in a while, we didn't find such metric. So bang. This was totally not working for the case we were solving. It totally deserves more attention later. We never actually gave it more attention, but it deserves more attention, but not now. We need to solve the task, and okay, it's graph theory time because unsupervised learning wasn't working and we didn't know what to do. So we reconnected components in the cluster. We've done that once with the membrane one. It worked amazingly cool. So we decided to do it again. Boom, that's actually a weakly connected component in a graph. Check it out in Wikipedia if you're interested how it's defined exactly. It's nothing too sophisticated. Yeah, so we decided to decompose the graph with it. And what happened? Okay, we take the weakly connected components. Imagine those are persons only connected to themselves and not connected to the rest of the world. So we found a few. We found a few weakly connected components, and the interesting part was that, imagine that one. Yes, imagine that one. So we have found clusters like that, and that's our leader. And there were a lot of components like that, and the center of the cluster were always leader. So it was definitely working well. And we decided how to decompose the graph more. So we decided first we use all of the interactions. Then we remove all the interactions which were lower. That decomposes the graph a bit more. Then we removed the medium interactions and then decomposed the graph a bit more. And after that, we decided to remove all the connections between users if they haven't had at least 2, 4, 8, 16 at the end of the day high connections. So when we removed it, a lot of clusters, 401 actually, were there. And the cool part was that in each strongly connected, weakly connected component, there was exactly one leader, and it was the center of the component. So this was definitely working. And when we combine it with the gateway clusters, because we totally should agree that if you are a gateway, the people connected to you are at your cluster, there were more than 600 clusters, which is not representative for all of the leaders, but it was giving us a pretty good idea and a pretty good structure. So we said, graph theory is working good here. It's working amazing here. And let's do something else cool with it. So, again, company and family detection. Again, I should say, if you see this, it should not be company or family. It's just an interesting structure in the graph that we decided could be a company or family. If it's a real case, to verify what is it, we would need a lot of data, a lot of domain knowledge to say, okay, this might be a family or this might be something else. But in that case, we just gave these interesting structures to you to think about it and to, let's say, investigate them because they are cool. So graph theory, don't bother too much about it. First, we use clicks, and that's a click. It looks very interesting. If people in that thing is connected to each other, and this is leading us to the conclusion that this could be something artificial, like company communication or something else, some maybe internet interaction. But if you have some of these, and they are with size more than 3 nodes, they are definitely something you should definitely check it out. But they look too artificial and not so cool, so we decided, can we define something like friends? That is a bit complicated graph theory, but imagine this structure or that structure. We can extract them They have a definition, check it out later. They look like communication, interaction between family or friends, because not everybody calls everybody, but they are really strongly connected. So we decided to find some of those to show you, just to know that there are such structures in the graph, and that you can explore them and with more domain knowledge find something useful. So now, we defined two membranes. We found the leaders. We found clusters. We are happy about the clusters. So what's left to do is group 5. And we decided to approach group 5 like the seed boards. And for the sake of my examples after that, imagine that seriously, group 5 are seed boards in our network, and we really need to identify them to stop them from doing what they are doing. We don't, I actually, it's the first time I've heard about churn detection was here at that presentation. So by the hackathon, we didn't really know what we were looking for, but it actually worked pretty good. So now, first, imagine there is a secret in your communication group, and you have a kid, and you really need to know if that kid is in danger, how close is that kid to communicating to a bad person, to a secret. So you can define a pretty simple measure. Just imagine if I'm connecting to Mishu, let's say, and he's connected to a seaport, then my connection to the seaport would be 1 to Mishu, 2 to the seaport. So we need closeness here, so we just reverse it. And it was pretty easy to find just the shortest path from me to some seaport, reverse it, and that gave us a pretty good metric that is represented how close I am to communicating with the bad people. So this doesn't say you are bad, it's just saying how close are you to communicating to the bad people. That's the distribution of the distance. So you can see most of the people are at 3 hops to the bad people. It was pretty interesting mathematical things in those data. At some point I will tell you, but not now, maybe never. Okay, so now the more interesting part was, okay, I know that my child is in danger to talk to seaport, but how can I define the bad guys in the network? How could I say, I know those two are bad, and based on them, I can tell that somebody's bad. So we can find, let's say, that Emperor and Star Wars a bit much easier than they actually did on them. So that's a decision tree. You've seen some of those already, and it's trained to recognize group 5. It is what a simple model, so I could explain it, but it just says, if you don't have a lot of connections, and you are a gateway, and you have a lot of high outgoing connections, you're bad. I know it doesn't make real sense to you right now, it does not make sense to me either, but that's what data says. And on the other side, you can see that if you have not that much unique connections, and you don't have a lot, and you have a lot of medium cost, you probably are bad. So those definitions are not necessarily white box. You don't have to understand them, but if you test your data and you have enough data, we let's say have enough data, you can see, here comes the confusion, that actually, probably you don't understand that, but those are, so that number is 97%. We've said to 97% of the nodes, you are not bad, and they actually was not bad. So that's good. That's good cover. That's a good number. So we can tell you you are not bad, and let's imagine it a bit stupid that if I tell you are not bad, there is 97% chance of you not being bad. And if I tell you you are bad, there is a, let's say, this is still not strict academical, but let's imagine if I tell you you are bad, there is 70% chance of you being bad, and there is 24% chance of you not actually being bad, and I'm to be mistaken. So this is not super impressive as a result, but based on the fact that we don't have domain knowledge, actually this works pretty cool. And with a bit more domain knowledge, it's pretty easy to build a sophisticated model that can say, are you good or are you a bad seaport or not? And if this is a true detection, actually, you can create pretty easily a system that is offline, so you just click reporting and see which users are in danger of that. And this could work with pretty nice numbers behind it. It could be always, not always, but in most cases, right? So this is something that totally could be applied in real life, of course, with a lot more domain knowledge. Okay, so now, Why is this to use supervised probability? That's how you make difference between data. You have somebody marked as bad, somebody marked as good. Supervised learning is the way to define them and to see what's going on. Even if it's a black box solution, if you don't understand why it's so, if it's working well, sometimes you don't care. So now, we've solved all the tasks. And what happened next was that we had learned something from that data. And the first thing we've learned is that graph theory is awesome. We really like machine learning and supervised learning. Graph theory works better in graphs usually. Unsupervised learning is hard because when you apply it, you need to know what you're searching for. It's a bad idea to just apply it and see what's going on. Sometimes it's not, but just think about it. It's something hard. You really need to know what you're doing when you're using it. Occam Razor is wise. Occam Razor is a problem-solving approach that says that the simplest solution is almost always right and almost always the best. And if you have some dealing with data science, at some point you will see that this is probably true. And that was awesome. Thank you for that to you all. It was a pleasure to work with such excellent experts. And last but not last, I was thinking during the whole day, I was thinking about a guy that said something, and finally I found it. So basically, that's some Canadian British journalist, expert in social networking, psychology, and other cool sciences. And he said that probably have all heard that at Facebook they said, I am away at 7 hops from each of the world. And this doesn't actually mean that we are pretty close together. It only means that a few special people are at the center of the world, and they are connecting us all to each person in the world. So basically, our leaders in the graph were something like that. They were the special people making the graph stay together.
Thank you.
So yeah, that's it. And if you have questions, now is the perfect time.
I have a question because we have on the last day we have provided you with the data of the real IDs where and you have matched them if you have matched with your leaders. What was the match percentage? 1800, 18 something.